Okay, so we're going to talk about trigonometric substitution, and where this stems from is, all right, you can do some integrals. Great. We can do substitutions, we can do integration by parts, we can do a lot of trigonometric integrals, but what if someone was to give you an integral like this one? Let's run through our list of things that we can do. Does this fit an integration table anywhere?
No.
Okay. Is a substitution going to work?
No.
No. Because if I substitute for this, the derivative is something with an x. I don't see an x. I'm not going to do it. Okay. Is integration by parts going to work?
No.
Not really. Because, well, we have a piece of an integral. This thing would be the other piece. That'd be bad. We basically do integration by parts when we have a product in there somewhere. All right, well, if we don't have that, is it a trig integral? Does it have sines or cosines or tan? Then we got to have something else. Here's the something else. The idea is, let's kind of change this. Let's think about this in kind of an out-of-the-box kind of way. Let me just consider the square root of 1 plus x squared. Now, somewhere along the way, someone said, well, wait a second. You know what? This looks a whole lot like Pythagorean theorem. Whole lot like it. In fact, this looks like I could do 1 squared plus x squared. Same thing, yeah?
Mm-hmm.
Well, then they said, wait a second. If that looks like Pythagorean theorem, the stuff that we would get by Pythagorean theorem, then maybe we can make a triangle out of this thing. So they said, well, I can't do it like this. Well, this looks really similar. So let's make a triangle and see if we can actually use that. Here's a crazy idea. So we create this triangle. And what we're going to do is we're going to fit this piece of junk that we can't deal with as one of the sides of our triangle. The whole deal that you're going to develop here in this whole section, I don't really want you memorizing a lot of the formulas I'm going to give you. There's only 3 of them. I don't want you to have to sit there and memorize with flashcards. I want you to understand the concept, what is actually happening here. What's actually happening is that we're going to take this and we're going to make it a side of a triangle. Now, there's a very specific way that you do this. You have to tell whether it's a leg or whether it's what's the longest side of a right triangle?
Hypotenuse.
Whether it's the leg or the hypotenuse. It's not hard to tell. What would this be, a leg or a hypotenuse? That has to be the hypotenuse. The only way that happens is if I have a leg squared plus a leg squared, then I take a square root, that gives me the hypotenuse. Remember this? A squared plus b squared equals c squared?
Mm-hmm.
Check it out. If it's this, hey, look at it. If it's this, then this thing stands for a hypotenuse. Are you with me on that one? If it's this, what's that?
It's a leg.
It's got to be a leg. Do I know which one? Well, we'll talk about that in a minute. You can choose. We'll pick correctly. There's only one correct choice, but we get to choose. Or if it's the other way around, that's also, oh, sorry, you know what? That was stupid. Same thing. I meant this. Or if it's that, that's also a leg. Do you guys get the idea here? So somehow we can fit this square root of something plus something, or something minus something, as part of a triangle. In our case, this says, wait a minute, the only way that I can make this fit a triangle is if this is the hypotenuse. And this is my angle. Now here's the deal. For the rest of your triangle, your idea is going to be to try to make the sides in some relationship that allows you to create tangent, sine, or secant, where you have a variable over a constant. So I'm going to do this. I'm going to say, wait a second. If this is square root of 1 squared plus x squared, can you tell me the lengths of these sides? It's a piece of cake. One of them's x, one of them's 1. That's it. Now, if I do this, 1 and x, that's a cotangent. Cotangent's really hard to deal with. Okay, you know what, I kind of skipped a point. We're going to use a relationship here that allows us to not work with this one, but work with a trigonometric relationship of the other 2 sides. So I don't like the square root, that's really hard to work with. So I want a trigonometric identity that lets us work with the other two that don't have square roots, the easy parts of this. Does that make sense? So I want to make it easier. If I do this 1 over x, well, then I'm not really going to get something nice. I'm going to get cotangent. Those don't have some nice, that does have an identity, but we try to stick with easier identities. So I'm not going to do 1 over x. I'm going to do x over 1. X over 1. Now, here's the plan. The plan was, if this is part of our triangle, and now we have our other two sides, x and 1, let's pick a trigonometric identity, trigonometric function actually, that allows us to relate the two other sides in a really nice fashion. For instance, if I look at tangent, tangent is, for this specific triangle, how much is tangent?
X over X.
X over 1, or tan theta is simply x. That's great. I really need you to get this idea before we go any further. I want you to really see what's happening. What's happening is we don't know how to do this. We take this part away. We go, you know what? That looks a whole lot like part of a triangle with Pythagorean theorem. Let's make it be part of a triangle by Pythagorean theorem. Then we can find the other two sides of that right triangle. Well, it's really easy. It's kind of given to you. One of them is 1. One of them is x. We put them in this relationship. That way, when we do tangent of our angle, we get simply opposite over adjacent. We get x over 1, or tangent theta equals x. Show of hands, feel okay with that idea. It will become more clear. I promise. There are a lot of examples. I'll also give you the formulas, but I'm going to teach this to you in a way that it makes sense, not that you just follow the pattern. Okie dokie? It does have to make sense to you. Now, it'll become easier if it does. This is what is awesome about this. You agree that tan theta equals x, correct? Tan theta equals x. Tan theta equals x. That allows us to do a trigonometric substitution. So we'll have an integral. We'll still have a square root. Notice we're not substituting for the square root. We can't do that because there's nothing to get the derivative away. Square root, we're still going to have a 1. Are we still going to have an x?
No.
No, instead, what is our x?
Tan squared.
So we're going to have tan theta, wait a minute, just tan theta?
Tan squared.
This was x squared. Hey, look at that. Tan theta is x. This becomes tan squared theta. I want to show of hands if you feel okay with this so far. Remember those times your Calculus 1 teacher, maybe it was me, told you, don't forget your dx, don't forget your d theta, don't forget those. Remember that? And how some of you still forget the dx and all that junk that you think is irrelevant? Here's what's not irrelevant. If you just leave that as dx, does this match your...
No.
This is an issue. These have to match. Your variables have to match. So what in the world do we do with that dx? It's really similar to doing a u substitution. Really similar. So we have tan theta here, we have x. Can you figure out what dx is?
Take a derivative.
Take a derivative. What's the derivative of...
Secant squared.
So secant squared theta equals how much?
dx.
Ah. Now we know. So this part becomes our dx. I'm going to work over here, but it's not a really complicated idea, but it's new for you. I know it's brand new. So I want to make sure that you guys are okay with exactly what's going on here before we go any further. You understand we can't do this the way it is, correct? Can't do it. So we pull it off. You understand that this is a hypotenuse of a right triangle. It's got the plus there, it's a leg squared plus a leg squared, and we take a square root. That is the distance of a hypotenuse. If we do that, it gives us one leg and the other leg, upon which we can make some sort of a trigonometric function, a relationship amongst those two sides. Tangent is the appropriate relationship here. It's nice. We don't want to do cotangent, it'd be 1 over x. That'd be silly. I want to do tangent and get x over 1. That way I have a nice substitution. So tangent equals x, tan theta equals x. We plug that in for x. So 1 plus tan squared theta, we still have square root. dx is an issue, we gotta change that. So just like you did on a u sub, you still take a derivative. So tan theta equals x, no. Let's do secant squared theta equals dx. Then we get, okay, cool. Integral of square root 1 plus tan squared theta What's else?
Secant squared theta.
Secant squared theta what? That's nice. This part, that is my dx. So instead of dx, I've got secant squared theta. Oh, you know what? I forgot my my d theta. Why didn't you guys catch me on that? We were sleeping. My goodness. Do y'all feel okay with that one so far? Look what it does. As soon as you do this, that changes into from 7.3 to 7.2. Just what we did. You just did stuff like this, didn't you? In fact, this is even nicer because it already has an identity built right into it. It's already going to match up. That's why we pick one of 3 trigonometric substitutions. We pick tangent, we pick secant, and we pick sine. If you got those 3, the identity's already there. It's really, really nice. You guys ready to do this thing? So tell me, what is 1 plus tan squared theta? Okay, we do need to know that one, all right? Do we have a square root still?
Yeah.
1 plus tan squared theta is secant squared theta times secant squared theta d theta. Give me something nice that happens. Do what now? Square. Yeah, that's exactly right. This has to happen. So this is nice because we have one of these identities which you are going to have. Look at it's being squared, right? It's squared. So you can have a constant plus something squared. You can factor that out. You can make it work so that with identity, your square root gets rid of your square. That's fantastic. We love that. So this becomes secant theta times secant squared theta d theta. What are you going to do now?
Combine them.
Probably combine. Oh goodness. We've actually seen this one before in class. Do you remember? We did. This was a horrible one. Actually, no. It was secant to the 5th. That was really horrible. Do you remember doing that one? We split it off. We used an identity. We did a whole bunch of stuff with it. We ended up adding the integral back and dividing. Remember that? So I'm not going to do that again. This is already in the video. If you want to refresh your memory on your notes or something, it's already back there. I don't remember if it was 7.1 or 7.2. I think 7.1. I think it was integration by parts is what we did. So it's already back there. But anyway, this integral becomes, was it 1/2? Oh yeah, that's what I couldn't find it. Yeah, 1/2. 1/2 secant theta tangent theta plus 1/2 ln absolute value of secant theta plus tangent theta. No reduction formula here. It's integration by parts if you really want to prove that that is the way it is. You'd split off the secant squared, you take the integral of secant squared, it becomes tangent, and then you do your integration by parts. You guys okay with that one? I'm not going to show it, it's already on the video, we've already done this one. Quick show of hands, feel okay up to at least this point. This one we've done before, so I don't want to rehash it. What I do want to say is, okay, let's take a look at my integral. Firstly, I don't know, I think this is really cool. Do you guys see how interesting this actually is that we can do this? We're using a triangle to do an integral. It's crazy, it's out there, it's kind of fun. Here's the problem. What variable did I start with? What variable do I have now? That's a problem. So, you're not done right here. Don't just put a plus C and go, I'm done. You're not done. But the rest of this is not that hard. You see, we've got this triangle that we created. Do you remember when you did a U-sub? When you did a U-sub, you used the substitution to change a part of your integral, correct? Then when you got done, you substituted back in. Remember that? Same thing happens here. We used our triangle to do a substitution. Now we're going to use our triangle again to substitute back. So if our triangle is the square root of 1 plus x squared, and this is x and this is 1, here's what I want to know. That's theta. Here's what I want to know. Can you tell me all of these trigonometric relationships? Just put that anywhere. It's fine. Can you use this triangle to tell me all these trigonometric relationships?
Yeah.
Yeah. So let's list them out. Can you tell me what secant theta is using? Now you got to be good at this. You got to know that tangent is opposite over adjacent, and sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. And you have to know what cotangent and cosine and cosecant are. So tell me what secant is.
Hypotenuse over adjacent.
Very good, because cosine is adjacent over hypotenuse, therefore secant, the reciprocal of cosine, is reciprocal of this. So what was it again?
Hypotenuse over adjacent.
Hypotenuse. What's the hypotenuse? Over?
1.
Let's also do tangent. So we're going to do all of our trigonometric functions right here, just right by our triangle. Can you do tangent?
X over 1.
Opposite over
Brilliant. Just opposite over adjacent. We got x over 1. Do your substitution. It's not hard. Tell me what's going to be here for me, please. What's going to happen? We got a 1/2. Very good. What else?
secant.
Secant. What's secant?
1 that.
Okay, then what are we going to have?
X.
Okay. Plus, what changes over here? Does the 1/2 change?
No.
No.
No. Does the ln change?
No.
No.
Does the absolute value change?
No.
What's inside?
Square root.
1 plus x squared times x.
Not times x.
Plus x.
Oh, it does.
Well, actually, you don't know what your X is.
And then?
Plus
90 plus c. Probably clean it up a little bit. I would at least. I would do,
1/2 x.
yeah, I'd do 1/2 x. You could factor out a 1/2 if you wanted to.
Oh, you did.
1 plus x squared, and then plus 1/2 ln absolute value square root of 1 plus x squared plus x plus c. Oh my goodness, let's check. Is it in terms of x like we wanted it? So the idea, kind of, okay, it's a crazy idea. It's a cool idea. It's use a triangle to make a substitution based on a trigonometric function. Do the integral like you know how to do. It's just a trig integral. You guys should know how to do this stuff. And then, at the very end, when you're all done with it, use your triangle again. So triangle to make a substitution, triangle to fix your substitution. Show of hands if that one actually made sense to you. Do you guys get the idea? Did you even know that was possible? Kind of cool though, right? Do you want some more examples? Of course you do. Yeah, of course. Now, this made it look a little bit easier than it might be for you because I skipped over this. I skipped over the secant cube. We did that one before, which you're fine to use that, okay? If you've done it before, look it up. Okay, we've done that. But you do know how to do that. That is an integration by parts. So some of these are going to take you some time. Do you guys have any questions? Because these problems take a little bit of board work, so I'm going to have to erase this. Any questions at all before we go on? You can ask if you want. No? All right. So before we go any further, I want to give you a rundown about when we can use this and why it looks the way that it does. So we can use this when we have one of 3 situations. I'm going to give you the formulas. Again, I don't want you to just blatantly memorize the formulas. You will, okay? You will memorize them. But I want you to understand why they are the way they are. Because it's really silly to do this stuff just by, what's my formula? It doesn't make any sense. I want you to get why it works. And that's important. So this idea does work if we have one of these 3 things. If we've got a square root of a squared minus x squared, or a square root of a squared plus x squared, or square root of x squared minus a squared. Our first one was of this form. Now, after we do that, we'll be using one of our Pythagorean identities. So then we use either 1 plus tan squared equals secant squared in one way or another, and or 1 minus sine squared equals cosine squared. Say what?
You stand up with the theta.
Oh, darn it. Thank you. So here's the big three. I'm going to look at these in more detail. We're going to understand why they are the way they are, why the formulas actually work, and then every time we go through one of these trig integrals, trigonometric substitutions for integrals, I'm going to rehash the same thing until it kind of sticks with you. So here's number one. Let's look at this. If we were to create a triangle out of this thing, I always draw my triangles in the same orientation. That way I have it fixed in my head. I don't want to get random triangles up here. It's got to be a right triangle, of course. I always draw it this way. Maybe you can do the same thing. I want you to think of what this actually is. It's going to be part of the Pythagorean theorem, but think about the pieces up here. Would this have to be the length of the hypotenuse or the length of a side? What do you think? It's got to be a side because it's got a minus in there. Does that make sense? Pythagorean theorem says the hypotenuse is when you take the sides and add them. A side happens when you take the hypotenuse and subtract. So what we know right now is that this is going to be the length of a side. You guys all understand the idea. It's got to be a side. Now, think about which one of these would be the hypotenuse. If this is a side, one of these pieces has to be the hypotenuse. What letter has to be the hypotenuse? A has to be. X can't be because the hypotenuse is the longest side, correct? So if this is the longest side, if X was the hypotenuse, I'd get a negative inside my square root, and I can't have that. You with me? So we look at this and go, wait a minute. If this is a side, one of these is the hypotenuse, the bigger one, the first one, has to be the hypotenuse. That's got to be A. Now here's your major idea for this whole thing, for this whole lesson. Once you figure this out, it's not hard. I mean, shoot. If it's got a plus, that is the hypotenuse. If it's got a minus, one of these is the hypotenuse. Is that clear for you? It's the first one. The bigger one is the hypotenuse. Now, here's your whole goal. Your next goal is you're going to make these sides in such a way that you get x over a for either tangent or sine or secant. Those are the only three that we're going to use. Tangent or sine or secant. So we figure out where the hypotenuse is. Then what we do is we make our sides in a relationship so that tangent or sine or secant gives us x over a. Is that clear for you? I'm going to write that out and make a little note here. So notice that you get to choose, right? Either this is going to be x or this is going to be x. Either this is going to be square root of x, a squared minus x squared, or this is going to be the square root of a squared minus x squared. You get to choose, but only one's the correct choice. So put sides in a relationship such that we get x over a for tangent or sine or secant. These are the three that we use. We don't use cosine. We don't use cosecant. We don't use cotangent. We use tangent, sine, or secant. And the reason why we do that is because the identities are really nice for those. It makes it easy. You guys with me on that one? So let's try it. So this is our idea. We want this. Let's give one of them a try. If I do this, if I put x here, the only way I'm getting x over a is if I use what, please? You got to know your trig. Cosine would give me x. Is cosine tangent, sine, or secant? Then that's a bad choice. So we figure out a hypotenuse first, and then you only have two options. X either goes here or x goes here, or the side goes here or here. if x goes here, if x goes there, can I make x over a with either sine or tangent or secant? Which one?
Sine.
Brilliant. Just fill up the rest of the other side with whatever it is. A squared minus x squared. That's the idea. That's the idea. Show of hands if you understand the idea. You see, most classes or most books just tells you, hey, if it looks like this, we're just going to do sine equals x over a. That doesn't tell you why. The reason why we're doing this is because when you create your triangle, we're going to do it in such a way that this gives us something nicer, something without a square root. That's what we want, something easy. So, if I've got an a for my hypotenuse, I get my choice of x. I'm going to choose it in such a way that tangent, sine, or secant gives me x over a. Then we write that appropriate trigonometric function. So which one are we going to use? Are you still with me? So we go, okay, cool. Then sine equals x over a. Sine equals x over a. And we always solve for x. We solve for x because that is going to be our substitution here. You guys with me? We don't have x over a's, generally. We have x's.
What do you say, theta?
I keep forgetting. I'm so excited about doing this. I keep forgetting my thetas. So dorky.
To forget our dx, you forget your theta.
I know, it's ironic, right? But since I'm the teacher, ha 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 ha. I get to mark you down.
Doesn't mean you're right.
It's true, it doesn't. That is true. That's what I have you guys here for, right? To catch me on all this stuff. So if we solve for x, just multiply by a. This right here becomes your substitution. Now you are going to get very good at this. And what you're going to understand is that when you see something like this, all you have to have is x equals a sine theta. You're going to have to draw your triangle every single time. I still do it for myself, especially because at the very end, we're going to have to substitute back in. So you're going to need that triangle. So draw it. Get used to the idea of drawing your triangle. Don't skimp out on this stuff. But this is where that's actually coming from. Just show hands, feel okay with that one. Good. All right. The next one, number 2. Let's talk about a squared plus x squared. Now, we actually already had an example of that one. Michael?
So we just skip the other trig functions because they're just difficult to use in this way?
You don't need them. We use the ones that work all the time. Those ones are the tangent, the sine, and the secant. Could you do it with the other ones? Probably. But we don't, because these ones work. These are the big three. This one takes care of tangent and cotangent. This one takes care of sine and cosine. This one takes care of cosecant for us. So otherwise we'd have the different identities. These ones work really nice. You guys ready for the next one?
Yep.
First thing we do, every time we see one of these that we can't fit on our table, that we can't do a substitution for, that we can't do integration by parts for, and that's not trigonometric, we do a trig sub. That means you're going to draw a triangle. So we draw our triangle here. You've got to be very good at telling me whether this piece is a hypotenuse or a side. What is that one?
Hypotenuse.
Very good. So this makes it actually pretty easy. Our hypotenuse is a squared plus x squared. Now, we get to put our sides in a relationship. We are either going to have, by the way, what are our two sides here?
A and
Good. It's not a squared. It's a. So if this was a 9, you'd be putting a 3. Does that make sense? Okay. So we have a and x. Where's the a going to go? Opposite or adjacent?
adjacent.
Good, because I'm not trying to make sine or secant here because those have to deal with the hypotenuse. I don't want that. I want tangent. Tangent's going to be this relationship. I don't want a over x. That would be a bad idea. What I want is x over a. So in our case, our substitution would be tan theta equals x over a. You okay with that one? Solve it for x. X equals a times tangent theta. If you look back at the example which I left on the board, left parted on the board, when we did this, when we did our substitution, that was it. X was 1 times tangent theta. That's what we had here. Then we squared that. Still okay with it? Let's talk about the last one then. Then I'm going to have to erase all this, so if you have any questions, you let me know. But again, I don't really care if you memorize these ones. The way I'm hoping to teach you is that the relationship of a triangle actually makes sense, okay? Then you don't have to memorize the formulas. You can just do it whenever without having to look at it as a formula. Okay, number 3. Okay, let's think through. Square root of x squared minus a squared. Would you say that x squared minus a squared is a hypotenuse or a side? What do you think?
Side.
It's got to be a side. So it's either going to go here or it's going to go here. I don't know yet until I determine where the what the hypotenuse is. So let's talk about what the hypotenuse is. What's the hypotenuse here? How do you know it's x? Yeah, if it wasn't, if that was not a hypotenuse, this would be bigger. When I square those numbers, I get a negative, and that's a problem. So x is the hypotenuse. Now, we got to put our sides, which are a. A is a side here. X is already taken care of. A is a side, and this whole piece is also a side. All right. Where's the A go in this triangle?
Opposite over.
Okay, let's try it. If I do opposite,
Oh, no.
sine would give us A over x. Do I want that?
No.
I want x over a. And I can only use tangent, sine, and secant. So let's see which one of those would work. Would tangent give me x over a? Would sine give me x over a?
Secant.
Okay, so if that doesn't happen, what's it going to be?
The A is going to be.
It's got to be secant, and the only way to do secant is to move the a from here to there. Secant is hypotenuse over adjacent. So if I say, hey, the x is the hypotenuse, guess what I'm using? Secant. Hello? That's the only way it works. So if x is the hypotenuse, I'm using secant. Does that make sense?
Yeah.
Then this is x squared minus a squared. In this case, you go, okay, well, let's make our trigonometric substitution. Let's make something so that our trig function gives us x over a. The only one that works here is secant. So secant theta is x over a. If we solve for x, our substitution becomes x equals a secant theta. In each of these cases, we've used a triangle, we've created a trigonometric substitution. After this, we take a derivative of both sides. That lets us change our dx into a d theta. dx, d theta. dx into a d theta. We do our substitutions, and then we have a trigonometric integral, which we just covered that section for. Get the idea? Kind of cool, right? What can't you forget at the very end of your integral to do?
Triangle.
Yeah, so we use a triangle to do this, we're going to use a triangle to undo this as well. It's time for some practice. This is it. This is the whole idea. If you get this idea, you're done. All right, it's practice. It's not as easy as I made it sound. All right, right now it's like, oh, this is a piece of cake. They do get a little tough. Mostly it's just working with the trig, and not the substitution. You guys should be almost pros at that just after looking at this. It's typically the trig integral that gets like, oh man, because you're going to be doing the last section stuff again. You need lots of practice here. You guys ready for some practice? Exciting? A little bit? I'm so excited with it. I don't know. It's fun for me.
Will we be able to do the whole section just knowing this?
We'll be able to do the whole section just knowing this.
Yeah, like is this pretty much like the bread and butter of the whole thing?
This is trigonometric substitution.
Talk about for the homework.
Or,
7.1.
yeah, sorry, 7.3. This is pretty much 7.3?
Pretty much it.
Okay.
Yeah. Which is, I think, unless there's anything else that I haven't. Yep, that's it.
So we could do our homework after.
Yeah, why don't we just end right now then, huh? Yay. No examples whatsoever. Fantastic. You know, one more thing that I want to put up here for you that I didn't put up. If you're going to do this substitution, you're going to be getting a sine squared. You see it? If you get a sine squared, then you're going to be using this one. You follow me? You're going to have something, something minus sine squared. You'd be using this identity. If you're going to have a tangent up there, you're going to have something plus tangent. You'd be using this one. Does that make sense? So let me write this for you here. So once we have this, the substitution that we would have is 1 minus sine squared theta equals cosine squared theta. This would be the substitute, the identity we'd be using. Once we have a 1 plus tangent squared theta, you'll be using 1 plus tan squared theta equals secant squared theta. This one, if you have a secant, look at this. If you made the substitution, you'd have secant squared minus something. If you have secant squared minus 1, we'd use secant squared theta minus 1 equals tangent squared theta. And those would be the follow-up identities that you're going to use here. Now, let's practice. Do you have any do you have this written down, everybody? Yes, no?
Yes.
Yeah.
Okay. Let's practice. Again, I don't care if you memorize the formulas. It's going to be obvious what you do if you understand the idea. So let's do some. How about this one? Go through these integrals, not just that we're in a certain section for trigonometric substitution. Go through them and see if you can actually do them without it. Okay, like if I give it to you on a test, I'm not going to tell you what to do. So go through it. See if you can do it with a substitution. If you can, cool, do it. See if you can do it integration by parts if it's really quick. And you go, okay, I can do that. See if you can do it with just basic trigonometry if it has sines and cosines up there. Do it. Go to trigonometric substitution, of course, if you have something like this, but try some of those things. Like if this was just x, and that was just x, I'd go for it. I'd go for a substitution. I wouldn't start a trig sub because it would be easier than that. Does that make sense? Okay, in our case we have, well, nothing but a trig sub here. What piece are we looking at to substitute? Yeah, so let's take a closer look at the square root of 9 minus x squared. But you know what? I'm not going to think about it as 9 minus x squared. I'm going to think about it as... almost begs the question, well, wait a minute, what if it wasn't 9? What if it was 7? Could you still do it?
Yeah.
Yeah, you got to think outside the box, though. If this was a 7, you could do something like the square root of 7 squared. That would give you 7. Does that make sense? It's harder, but generally we get those perfect squares, which is really nice, but you don't have to. Okay, here's where the rubber meets the road. Basically, all you have to do is know how to draw your triangle. I mean, not just a triangle, but know how to put the sides on the triangle. That's the key thing. If you can do this correctly and make the appropriate substitution, everything else falls into place really nicely. So let's walk through it. I don't want you to just look at your notes and memorize the formula. I want you to think through this. Would you say that this is a side or a hypotenuse?
Side.
It's a side, for sure. Can you tell me what the hypotenuse is here?
3.
So create a triangle. That's 3. Tell me what one other side is.
X.
Now, we want to put this in a relationship so that we get x over 3 with what 3 functions are we looking at? I heard a lot at once. Hopefully you said sine, tangent, and secant. That's right, sine, tangent, and secant. Let's see which one would work for us. Is tangent going to put x over a for us?
No.
Tangent would put whatever, you're going to have a square root somewhere. That's not good. Would secant work for us? No, secant could put x over, 3 over x, but not x over 3. I don't want to do that. So what's the only other option for us? Sine. Let's make this work with sine. X would have to go there to work with sine. Does that make sense to you? The other side, now we change it back to 9. Square root of 9 minus x squared. Let's go for this. Let's do our substitution. So the first thing we got to do is, well, all right, once we have our triangle, what's our relationship again? One more time. What do we have?
3 sine theta equals that.
Good. So sine of theta equals x over 3. That makes sense, doesn't it? Sine of theta equals x over 3, opposite over hypotenuse. Therefore, x equals 3 sine theta. Quick show of hands if you're okay with that one. Cool. Now, what else are we going to do right now that we've done our substitution? Yeah, that's a great idea. So, dx would equal
3 cosine of
D,
theta.
I mean D theta.
So, hey, we got our substitution. Are you guys okay with this so far? We've got x equals 3 sine theta, no problem. Take a derivative. Dx equals 3 cosine d theta. Now we get to substitute with all this stuff. So let's see how it works out for us. In this type of process, everywhere you see x, you're going to have to substitute. There's going to be no elimination of x's because you're getting rid of all the x's with your thetas. So tell me what's going to be on the numerator, please. We got to move a little quicker here. What?
Sine squared.
3 what?
3 sine.
9 sine.
Okay, so 3. Is the 3 going to get squared here?
Yes.
Yes, it's part of your x. So this whole thing gets squared. If you put 3 sine squared theta, you missed out on your constant. You're going to miss that. Denominator.
Square root of 9 minus.
9's still there. Very good. What's
Minus 3 sine of theta.
3 sine theta and then what?
All squared.
All squared. Very good. I like it. And then, oh man, we got a d theta as well. Or sorry, dx as well. What's the dx become?
3 cosine of theta.
Okay, honestly, if I did this at the start of class, you'd probably be like, what in the crap is going on here? But let's see if it makes sense now. Are you guys okay with the triangle? It's just a triangle. You got to be okay with triangles. They're fun. Make up the relationship such that this fits okay, and that you get a trigonometric relationship you want. Sine, tangent, secant, where you get x over a. That's the whole deal. Once you get that, everything else works out real nice. So we got, well, most of the time, we got dx equals 3 cosine d theta. That's where this comes from. We got x equals 3 sine theta squared. 9, cool, minus 3 sine theta squared. Now it's just a matter of simplifying. Don't try to work with it now. Simplify what's going on here. So let's do it. This becomes 9 times sine squared theta. This becomes the square root of 9 minus 9 sine squared theta. And this is still 3 cosine theta d theta. We're just doing some algebra right now. Now here's the issue. This is almost an identity, but it's not. Why is it not an identity?
It's not
This time.
one.
The 9's are there.
You
Well,
can factor them.
let's factor the 9's. Yeah, let's factor that out. So 9 sine squared theta over square root of 9. If we factor those 9's, I get 1. Oh, beautiful. Look at that. Love math. Cool, that's the same. This, we factor out the 9's. We got 1 minus sine squared theta, we got 3 cosine theta, d theta still. You guys still okay with it? Tell me what happens when I have a product within a square root. What can I do with that?
Pull it out.
Yeah, you can separate products within square roots. So, let's see if we can do
Pull it out
this.
as 3.
We've got 9
1/3.
sine squared theta. We've got, what's the square root of 9?
3.
And then the square root of 1 minus sine squared theta. And then we got up here a 3 cosine theta d theta. 3's are gone. 3 here, 3 here. Also, check it. 1 minus sine squared theta. This is why we did that substitution, because this will work for us. So 1 minus sine squared, what is 1 minus sine squared theta? That's why we use sine, okay? Because that works nicely for us. Also, what else is going to happen?
Pull the 9
Square
out.
root bar.
Okay, so 9 is here. I've got sine squared theta. I have square root 1 minus, oh, sorry, I messed up. I've got cosine squared theta times cosine theta d theta. We still okay so far? It's getting nicer. Notice, have we done any calculus right now?
No.
Not really, at all. All we've done is manipulate it. So we've got 9 out front, 3's are gone. This is cosine squared theta, it's still in the square root. Tell me what happens with that square root.
Cancel. And then the cosines cancel.
Sine squared, yeah.
So we have cosine theta times cosine theta d theta. Those are gone. We have 9 integral of sine squared theta d theta. Can we do the integral of 9 integral of sine squared theta? How would you do it?
Reduction formula.
You could do reduction formula. You could. How could you do it if you didn't want to?
Wait.
They have main part.
Say what?
They have
Half angle. Yeah, very good. Sorry, I didn't hear you. So if I did half angle, we could do 1/2, 1 minus cosine 2 theta d theta. One half minus 1/2 cosine 2 theta d theta. Stop me if you see a mistake. I know I'm working kind of quickly here. What else? What else?
Pull the 1/2 out.
You could pull the 1/2 out. Then we're going to have 9/2. If I factor the 1/2 out, 1 minus cosine
Yep.
2 theta d theta. Don't just pull this 1/2 out though. You'd have to factor to make that happen.
Why didn't you do it on the earlier stuff?
You could have. Yeah, you totally could have. Don't know why I didn't.
Oh, you're talking about that right there.
Yeah, you could have done it right here. Just pull the 1/2 out.
I didn't see that, you're
Yeah.
right there.
Can you take the integral of 1? What is it? It's not x, no. Keep in mind, this is why that's important. Theta. What's the integral of cosine 2 theta? Good. So theta minus 1/2 sine 2 theta. Are we still okay? Okay, we're going a little long today. I'm sorry for that. Do you guys want to finish it right now?
Yes.
Okay, so, I bet you do. We had no class coming in, so we're good. Woo! Let's go another hour.
Okay.
No. Just joking. We're not doing that. I'm hungry. I'm wasting away. I lost 3 pounds in a week. I know, I've been moving. It's been crazy. Anyway, that's not important. So, theta. Don't you feel sorry for me? I have to do math and I'm moving? 1/2 sine 2 theta. We still all right with that one? Now here's the issue. This is done. Calculus is done. But we started with, we have, use your triangle. You're always going to use your triangle. So, here we go. Let's start with it. What do we know about this thing?
We know what sine is.
Oh, goodness gracious.
Theta, then solve for theta.
X equals 3 sine theta.
Well, we know that sine theta, let's start with this, okay? Because you can't have any thetas left. You got to have all x's. We know that sine theta equals x over 3. We know that, don't we? Okay, cool. So keep it simple. Use this substitution again. Sine, this is why we write this one. We don't go directly to this one, because oftentimes we'll have to use this. Sine theta equals x over 3. If that's the case, the only way we can solve this is say, well, let's take a left inverse of sine on both sides. If we do this, sine theta equals x over 3 if and only if theta equals sine inverse x over 3. That's one little piece. Here's the problem. Our main problem. Our main problem is that sine 2 theta, that's a problem. If I look at sine 2 theta, is that 2 theta?
No.
No, you don't just get to pull out a 2 or multiply something by 2. You actually have to have the actual theta. So when we look at sine 2 theta, we need to know that that is the same thing as 2 sine theta cosine theta. Hey, look at that. Do you recognize that identity? Sine 2 theta, yep, is a double angle. So sine 2 theta is the same thing as 2 sine theta. Now it becomes easy. Can you do sine theta?
Yes.
We already know that one. Sine theta is x over 3. Let's do cosine theta. Let's look back at our triangle for cosine theta. How much is cosine theta?
Opposite like so.
Adjacent over
Adjacent over hypotenuse.
x over the square root of 9 minus x squared.
No.
Square root of 9 minus x
Cos.
squared.
It's all
Adjacent
nine.
over-
So
Adjacent over
ca,
hypotenuse.
ca.
Adjacent over
Adjacent over
hypotenuse.
hypotenuse.
Adjacent over hypotenuse.
Like, hello, guys.
Right.
You like our cheerleader back there? So good, totally, guys.
It's okay, you can use
Do
fingers
it.
to count. It's like-
Yes. Okay, I'm gonna have to erase this. We're gonna move over here. We're almost done, I promise. But I want to make sure that this actually makes sense to you. Are you okay with our triangle substitution for this? That was pretty. This is the easiest part, actually. Is this? It's the easy. Now that I've taught you how it actually makes sense, you don't have to follow the formula. Hopefully, you understand hypotenuse, sides, put them in the right relationship, get whatever trig substitution is necessary. Everything's simplification. All of it is simplification until right here. Then we have a little bit of calculus. You know how to do that already. That's your last section. We get all the way down to here, and then you go, junk. Now we got to substitute back in for any thetas that we see. Some of them are easy. Some of them are take some time. Okay. So check it out. Theta. Whenever you have just a theta, you are going to have an inverse trig function. So if sine theta equals x over 3, theta is sine inverse of x over 3. You got it?
Yeah.
Sometimes you'll need an identity. Sine 2 theta, no, can't have that. You get 2 sine theta cosine theta. Well, sine theta would be x over 3. That's from our triangle. Sine is x over 3. Cosine theta is square root of 9 minus x squared over 3. And now we're going to put everything back together. So, nine halves. We've got theta minus 1/2 sine 2 theta. I'm going to draw it out to make it hopefully very clear for you. This is 9/2 theta minus 1/2 times 2 sine theta cosine theta by the identity that we just used. So the 1/2 is here. This is 2 sine theta cosine theta. Understood? 1/2 and 2 are gone. So we get 9/2. Theta is sine inverse x over 3 minus sine was x over 3, cosine was square root of 9 minus x squared over 3. We'll make it just a little bit nicer looking here. You could factor out a 1/9, but don't do it with this 3 because that's part of your angle now. You can't change that. So, oh, not angle, that's side relationship. So 9/2, we'd have sine inverse x over 3 minus x times the square root of 9 minus x squared over 9, and then finally plus c. Oh my goodness. Yay! Is the triangle the hard part?
No.
No, it's all of this junk that hopefully afterwards. I need a show of hands if you feel okay with what we just done. Fantastic. All right, 3 more examples and we're done with section 7.3. Again, we're going through some of these integrals that we can't otherwise do without this thing called trigonometric substitution. So the idea is look for a square root in your problem. Sometimes you will have to create a square root in your problem. If you look for a square root in your problem that fits the Pythagorean theorem of a right triangle, we can do the substitution. So let's take a look at this one. This one's not going to take us too long. I just want you to see a couple other techniques that we're going to use here. So integral from 1 to the square root of 3 of 1 over 1 plus x squared to the 3/2. Do we have a square root in this problem?
Yeah.
Might be a good idea to write it like that. So instead of just like this, just take a second and rewrite it so that we have that square root. So instead of 3/2, what does that 3/2 actually mean?
To the cube. Or to the third power.
Square. Okay, so I'm going to have a square root like this. And then what I'm gonna do is I'm gonna have that 3 outside. You should know from your algebra that you can have the power 3 inside or outside. We're gonna choose the outside, that way our substitution is actually possible. You guys okay with that so far? Now, we should be to the point where you can make up your own triangle here. So give me the idea, let's walk through this one, I'll have you do the next one on your own. What's the idea? What are we trying to do?
That's the hypotenuse, so we want to find the leg.
Okay, so we want the legs and the hypotenuse. Let's look here, we get the square root, and what I'll do is I'll have square root of 1 plus x squared. That's going to give me something here. So we're trying to make the square root of 1 plus x squared be either one of the sides, one of the legs, or the hypotenuse. Now, one thing I'll always do is I'll try to write whatever this number is as a square. That way it gives me the side, one of the lengths of the legs. So instead of 1, I know it seems a little bit trivial, but I'll put 1 squared. If it was like 4, I'd put 2 squared. 16, I'd put 4 squared. That way I'm not accidentally putting the wrong number on one of my legs. Does that make sense to y'all? Okay, so let's think about it. We got the square root of 1 squared plus x squared. You guys should know right now what that is, whether that's a hypotenuse or the length of a leg. What do you think that's going to be? How do you know how do you know automatically what it is?
Pythagorean.
Okay, if it's got a plus there, it's got to be the hypotenuse. Not because it's a formula, but because we understand what the Pythagorean theorem does. Pythagorean theorem says that the length of the hypotenuse is 1 leg squared plus another leg squared, and then you take a square root of it. So there's no way that can be a leg. This has to be the length of the hypotenuse. Does that make sense to you? If we have a minus, well, that's the other case. Pythagorean theorem says for the length of a leg, you're taking the hypotenuse squared minus another leg. So what we know is if we had a minus right here, this would give us the length of the hypotenuse, and this would give us the length of the other leg. This would be the length of the last leg itself. So let's go through this. How much do you know about what trigonometric identity to make? Which 3 do we always use? Good. Those are only 3, because those are the identities that work well for this. Now, what we're trying to get out of this is x over a constant. X over a is what we say. So we got to use either tangent or sine or secant to make this happen. In that case, we're going to pick x for here and 1 for here. So we look at the length of our sides. We got x and we got 1, x and 1. Where's the x going to go? Here? Option 1, option 2?
Option 2.
Option 2. Let's try it. We'll put x here.
Oh wait, no, option 1.
If I put x, well, let's think about why though. Don't just fall into the pattern of look at the formulas. I hate that. I don't want you to memorize all the formulas and okay, because what if you forget a formula? That sucks. If you understand the triangle, it will make this easier. Let's look at this. Firstly, do you all understand why this has to be the hypotenuse? Yes or no? Okay, if that's the case, either this is 1 and this is x, or this is 1 and this is x. If I have this, is there any way in the world I'm going to want to use sine or secant on this triangle right now? Sine, I'd have this. I'm trying to get rid of that. That's the whole idea. I don't want that. How about secant? I'd have this. I don't want to use that either. I want to relate the easiest 2 sides, the x and the constant. But I want to do it in such a way that I get x over the number, not the number over x. So is this going to work for us?
No.
Tangent would give us 1 over x, but, well, let's make it nicer. Let's put x here and 1 here. Now, if I take tan theta, I get x over 1, which means that x equals tan theta. Typically what we'll do is remove our constant over here, since it's 1, no big deal. Okay, keep on going. What now? We got x equals tan theta. What's the next idea? Before we plug it in, because we have 2 things that we're going to be doing here. What else are we doing? Say what?
Using the derivative?
Let's do that. If we take the derivative, you see when we do this, we're going to be changing this into some sort of a function involving theta, but we also need to change our dx into some d theta. So in order to do that, we take our derivative, we get dx equals, oh everybody, tangent. D theta. Perfect. Guys, so far so good? Go ahead and make the substitution. Let's see you guys do it. Go from here, plug in what you need to plug in. I'll do the same thing on the board. I just want to make sure you can do it on your own, okay? So go. I'll give you about 10 seconds, then I'll put it on the board. Make your substitution. notice when you're doing trigonometric substitution, the square root, it's never going to change. The idea is that we're changing just this variable x, because when we square it, when we square whatever that variable is with our substitution, we're going to get some sort of 1 plus or constant plus that we're going to be able to make an identity out of. Like 1 plus sine squared, or 1 plus tangent squared, or 1, it's one of those things, actually it's 1 minus sine squared, sorry, or 1 plus tangent squared that automatically fits one of the identities that we have in hand. So does the 1 change?
No.
No. And the plus doesn't change. What's the x become?
Tangent squared theta.
Good, so if the x is tangent, then this is tangent squared theta, very good. And we still have that power 3. Let's make sure we're not losing anything. Now, the reason why we did our derivative right here, so we also substitute for our dx. What's our dx become?
Secant squared theta.
Let's make sure. Do we have all thetas and a d theta? Looks like it. We're pretty good to go. There's one thing I haven't done yet, and this is kind of up to you. I like doing this. Some people don't. Some people like to wait to the very end. I like changing bounds. I like to because sometimes I'll forget to re-plug in my substitution. That kind of sucks. So right now I'm going to go ahead and change bounds. We do that at this step. We don't want to wait till later. Do it right now when you're doing your substitutions. So right up here we'd have x equals square root of 3 and 1. Write that down. So, if that's the case, if x equals a square root of 3, then what we would get is tan theta equals square root 3, and tan theta equals 1. Please note, I'm doing this on purpose. I want to make sure that you guys see how to actually change the bounds in this scenario. If you have x equals the square root of 3, look at where the x is. X is not theta. What we're trying to do is solve for theta. Does that make sense to you? So we'd have the square root of 3 equals tan theta. We would have 1 equals tan theta. You guys follow this idea? Well, now what we're going to try to do is put our integral in terms of theta, not tan theta. We don't want 1 and square root of 3 here again. What we're going to have to do is use an inverse tangent to figure out what that is. So basically it says, okay, cool, I'm glad you got this. Now, go one step further, figure out how much theta is. So recall, I'll do this on one of them. Have I lost you? I don't want to lose you yet. Recall that this is true if and only if this is true. Do you remember doing that? This is true if and only if this is true. So basically it's asking, hey, what angle does it take for tangent of that angle to equal 1? And same thing here. What angle does it take for tangent of that angle to equal the square root of 3? Do you guys know what it is? Or can you think of the inverse? What's tan inverse of the square root of 3? What's tan inverse of 1?
Pi over 3 and pi over 2.
Pi over 3 and
Pi over 4.
over 4.
Pi over 4, yeah.
It's a nice order for us too. So this becomes pi over 4. This becomes pi over 3. Let's make sure that you guys all have this. Are you okay on writing this as a square root to the 3rd power? Yes, no?
Yes.
You guys are dead today, huh? My goodness. I know it's Monday, but geez. More activity. I'm excited about this stuff. You should be too. Goodness gracious. This is fun, I guess. Come on, people. You're talking about math Jedis already? Jeez. Okay, so are you okay with writing that as a square root to the 3rd power?
Yep.
Still wasn't any better, was it?
Mm-hmm.
Yes.
Lame. People in the video think you guys are lame
Right.
right now. Right on. Okay. Anyway, so this is now the hypotenuse. We already talked about y. We're trying to make our sides in a relationship that work with tangent or sine or secant. They give us x over a constant. We've done that with tangent. So tan theta equals x, no problem. Now, if you have a definite integral, change your bounds here. If we change our bounds, x equals square root of 3, okay, tan theta equals square root of 3. That's what we're getting. That means that you're going to have to do tan inverse of square root of 3 to figure out your angle. In this case, we get pi over 3. In this case, where tan theta equals 1, pi over 4. Tan of pi over 4 gives you 1. So we've changed our bounds. from pi over 4 to pi over 3. And it's still in order, which is nice for us. Okay, next step. Come on, tell me what we're going to do.
Secant squared from the bottom.
From the bottom. So we're going to use our identity. Get rid of that thing. This is always going to happen if you do your trigonometric substitution appropriately. You're going to have an identity that you'll use. So we'll have pi over 4 to pi over 3. Got a secant squared theta over, tell me what this is going to be exactly. What's still there?
Plus 1.
Okay, square root's still going to be there. I like that. What else?
Cube.
This is an identity. This is equal to secant squared theta. And what else?
Cube.
Don't forget any little pieces here. Cool, almost done. What's the next thing that we're going to do? Quickly, come on.
You could
Take it out of the
take away
square
the,
root. And
you'd end up with 1 over the square root of the secant squared theta to the second. And then the square roots would cancel out, you'd end up with 1 over.
Okay, so let's simplify this part. Let's do that. Square root of something squared, what happens?
Take away the 5.
Gone. So we got pi over 4, we got pi over 3, we got secant squared theta, we got the square root of secant squared is just secant, but then I have it to the third power. So this gives me secant theta to the third power. Are you still okay so far?
Yeah.
Notice all the simplifying you're doing? Really, we haven't done any calculus. This is a calculus idea, sure, trigonometric substitution, but have we actually done any, maybe a derivative here, huh? Maybe a little bit, but that's pretty easy. We're just really simplifying a lot of this to make it nicer for ourselves. So pi over 4, pi over 3, we're going to have 1 over secant theta d theta. Don't get hung up on this stuff. Think back to what I told you about trigonometric integrals. How trigonometric integrals work is this. If you have sines and cosines, I told you how to deal with those, right?
Yeah.
If you got tangents and secants, I told you how to deal with those. If you have cotangent and cosecant, I told you how to deal with those. If it's not one of those things, try changing it into sines and cosines. Try changing that. If it doesn't fit, man, what's 1 over secant? Well, let's think about 1 over secant is cosine. So pi over 4 to pi over 3, no problem. This is just cosine theta, and all of a sudden we have a very, very easy integral to do. Everybody, what is the integral of cosine theta? What do you think?
Sine theta.
Perfect. Oh, you got everyone now. Oh, I see.
We woke up.
Sine theta. Now here's the question. Do I have to go back and change everything into x's again?
No.
This is why you'll want to change bounds here, because if you don't, you're going to have to use your triangle. You have to go back and change this back into x's before you plug in 1 to the square root of 3. Did you just catch what I said?
Yes.
Okay, so if you change bounds, this is kind of nice here because you don't have to go back to your triangle. If you didn't do this, right now you'd be looking at sine theta. You would have x, look at this please, you'd have x over this, square root of 1 plus x squared. Then you plug in the square root of 3, and you plug in 1, and you subtract those two fractions. Does that make sense to you? If we change bounds, no big deal. We change these from x's into thetas. Hey, it matches now. So now these are in terms of theta. No need to plug it back in. We're just going to go pi over 4 to pi over 3. What that means is we'll have sine of pi over 3 minus sine of pi over 4. That should be pretty easy for us at this level. Sine of pi over 3 is what? All I heard is 2. It's over 2. That's good.
Square root of 3 over 2. Isn't the integral of cosine negative sign?
No, it's not. But think about what? Okay, square root 3 over 2. Very good. And
Square root of 2 over 2.
square root 2 over 2. Make them one fraction. Square root of 3 minus square root of 2 over 2. That's the idea. Took us a little bit longer than I thought, but show of hands if that one made sense for you. Good deal. Okay, let's work on the next one. So definite integrals, You might definitely want to try to change your balance here. That way you don't have to use your triangle to make your resubstitution. Just a good idea. Are you guys okay down to this far? Show of hands if you are. Very good. That's fantastic. That's what I'm looking for. Let's do the next one. Questions, comments, concerns? Is it more understandable than the first time we went over?
Yes.
It's getting easier. Is it getting easier for you?
I like definite integrals better.
These ones?
Yes.
Why?
There's no resubstituting.
That's
that.
why. That's why you change your balance. Well, of course, Rob, now that you've said that, I'm not going to give you any more definite intervals. We're going to practice these ones now. You're welcome. Okay, here's what I want to do. I want you guys to try to do this problem basically completely on your own, but we're going to do step by step. So the first thing I want to do, I want to see if you understand that that's going to be a trigonometric substitution. Can you see it just by looking at the problem? We're looking for, well, substitution firstly. Substitution ain't going to work. We're looking, is it by parts? Well, not really. We don't have a product that's going to work for us very nicely. Is it a trigonometric integral? Well, not yet. Well, we're going to make our substitution. So I want you to pick the piece that's going to be the trigonometric substitution. Go ahead and do that now. Pick the piece that you're going to use. It's always a square root. Always. If there's no square root in the problem, you need to make a square root in the problem. You can do that algebraically. So pick a piece of that that's going to be your substitution. Make a triangle from it. Make a triangle. Think about the piece that you just picked. Is that the hypotenuse or is that a leg?
A leg.
Okay, so you have it as a leg. Pick the appropriate piece of this that's the hypotenuse
X.
first. So label that out. Do it individually. Do it on your own. Let's see if we all get the right triangle. Do you guys know that making the triangle is like the most important part here? After that, once you translate it to a trigonometric integral, it's pretty straightforward. I taught you how to deal with it. The triangle is important here. I want to make sure you all got this. So right triangle. The piece you should have picked is x squared minus, I'm not going to write x squared minus 4. What I'm going to think of it as is x squared minus 2 squared. Okay, now let's think about it. Did you find out that this is actually the length of one of our legs?
Yes.
Okay, now how we start this, we always start with the hypotenuse first, always, because then we can determine what our legs are after that. So, if this is a leg, then one of these pieces is going to be my hypotenuse. Everybody, what is my hypotenuse in this case? Very good. Yeah, it's always the one that comes first. Otherwise, you have a negative inside of your radical. That's not possible. So, x is our hypotenuse. The reason why we write this as 2 squared rather than 4 is so that we don't accidentally put 4 here or 4 here. We put 2 here or 2 there, depending on which side that we need to use for this. Does that make sense to you? Okay, now, we'll think a little bit harder. Which trigonometric relationship would we want to use here? Would we want to use tangent at all?
No.
No.
Tangent's going to have a square root in it, and that sucks. I don't want that. Are we going to use sine?
No.
Sine would have x in it, but it'd be something over the x. This is the way you go through it. You actually think about these. Don't just follow the pattern. Think about what's going on here. Tangent sucks. It's got a square root. No deal. Sine's pretty close because we could make it constant over x, but I don't want it over x. I want x over something. So the only other option that we have is...
Secant.
So set up this triangle so that secant is going to work nicely for you. Where does the square root go? Bottom leg, right leg.
Right.
That way we get it out of the secant relationship. So the square root is x squared minus 4. I'll put the 4 back because I don't need to worry about that anymore. And this one, what's this going to be?
2.
2, not 4. 2. Do you understand why it's 2? This is why we do that. Well, let's make sure this works for us. We have hypotenuse, got it. We have one leg here. This is going to set up our secant relationship. And then we have this as another side. Show of hands, feel okay. Cool. Okay, go do the next step. If you haven't done it already, write the trigonometric relationship we just talked about as equal to those two sides. Find your derivative and make your substitution. I'll give you about 30 seconds to do that if you can do that. Okay, which one works again?
Secant.
Yeah, secant's going to give us hypotenuse over adjacent. So secant theta makes that relationship that we want. We want x over some sort of constant. Then what do we do after we get x over some constant?
Sulfur.
Yeah, solve for x because that's going to be our substitution. I don't see any x over 2's over here, neither do you. I see just x's. So let's make this x equals 2 secant theta. Okay, everybody, what's the next thing that we're going to do?
Take the derivative.
Yeah, because not only do we have to substitute for our x's, we also need to substitute for our dx. So by taking our derivative, by the way, just a question here, should you use a product rule here?
No.
No, it's a constant. Don't make things harder than they are. Don't do something silly, okay? I know that a lot of people think that this is going to be a really, really hard class, and in some parts it is, but don't make it harder than it is. If it's a constant, you wouldn't do this. What's the derivative of 2x? Product rule! Let's do it! No, that's silly, right? Yeah, it's a product, but that's a constant in front. It's a factor that happens to be a constant. So we do 2, and then what's this become?
Secant.
Theta.
Oh, theta. That's good. And then d theta. Very good. Okay, if you haven't done so already, make your substitution. Have you all substituted on your integral? Not yes or no? Yes.
No.
Have you made it that far? Okay, go do that next. Do the substitution. Let's make sure that we're all 100% correct. There's a lot of pieces here, lots of stuff going on, so make sure we're all right. Where you have x, what are we putting in for x?
Secant 2, secant.
Oh,
Two
close.
secant theta.
Don't forget that 2. If you forget the constant there, is your integral going to work out?
No.
It will, but your constants are all going to be wrong. So make sure your constants are correct. If it's 2 secant theta, make sure that goes in every place for x. And your dx, make sure we have the correct thing for dx. So let me make sure you get the same thing I'm about to get. Let me have your eyes on the board here real quick, please. So x squared, I still have a square root, but x squared, no. For x squared, I'm going to have this whole thing squared. Notice, it's not this. Do you see why not?
The twos.
Yeah, when I have x, this whole thing is the x. So when I square it, it's got to be like that. Did you catch that? That's going to affect this, because what happens here is when you square the 2, it allows you something to factor out. You can take that 4 out of there, and that's what we want to do. Also, to the 4th, well, it's now going to be 2 secant theta all to the 4th. So we got 2 secant theta, no problem, we got it squared. Minus, 4, 4, got it. We got a square root around it. We got a 2 secant theta, now it's to the 4th power, and lastly, what else do I need up there?
Dx.
Substitution for dx. So 2 secant theta tangent theta d theta. What I want to know is show of hands if you got exactly that on your paper. I know you do now, but like before I did it, how many people had that? That's good, that's great, that's the first step. If you didn't, does it make sense how to get that? Are you sure? It's going to take some practice, right? We got to get this stuff down. What's the next thing that we should do? Should we start doing substitutions and all that stuff right now?
No.
What are we going to do?
Simplify.
Always simplify these things. Don't do substitutions or crazy stuff until you have this simplified. So if we simplify, well, it's just a whole bunch of algebra. I'm going to go through it kind of quickly. If you have questions, of course, let me know. When we square this, this will be square root of 4 secant squared theta minus 4 all over 2 to the 4th is 16 secant to the 4th theta. And then of course we still have a 2 secant theta tangent theta. We can't afford to lose any of this stuff. Our integral won't work out. Next thing, what would you do if this was your problem on a test? Because it very well might be. What do you
Factor the inside of the...
Yeah, what we know is that identities work with secant squared minus 1, not secant squared minus 4. So when we have the same number here, that's what we have to have. That's important. We got to have that. So if we miss the 2 here, you're going to miss the 4 here. That's a problem. So once we factor that 4 out,
Let me pull it out as 2.
sure. I'm going to actually do that step right now, okay? So watch carefully. This 4 factors, correct? So what we get is a secant squared theta minus 1. If I factor the 4 and take a square root, it's going to give me 2. Does that make sense?
Yes.
This is this, to me in my head. Is it to you in your head?
Yes.
Okay, so secant squared minus 1, no problem. The 4 is factored. I take a square root because we can separate square roots like that with products. Over 16 secant to the 4th theta times.
2 secant theta tangent.
You'll notice that when I'm doing this, I'm not doing a whole lot of math in my head. There's a few things, but not a lot, because I don't want to lose any constants. That's the big deal. No losing constants, no losing negatives. Tell me some things I can do now.
Pull out the 1/8.
Turn it into a tan.
Okay, let's be careful about that 1/8.
Wait,
No, 1/4.
yeah, 1/16.
It's going to be a
1/4.
1/4. What, a 1/4.
Oh wait, shoot, yeah.
2 times 2 is 4. 4 over 16 is 1/4. So 2, this is 4 over 16. 1/4 comes out. Integral of, so this is 1/4. All the constants are gone. That's what we want. How much is secant squared minus 1? Everybody, come on. How much is secant squared minus 1? It should be an obvious identity because that's what we were going for. That's why we did our substitution in the first place. Once we get, hey, look at that. Something squared minus 1, this will become a 1. Something squared minus 1, that's great. We want secant because we know secant squared minus 1 is tangent squared. A square root of something squared goes away, gives us just tangent. This is the whole idea, folks. That's why we're using sine and secant and tangent, because those identities are so nice for us. So we got, let's see, square root of tangent squared theta over secant to the 4th theta times secant theta tangent theta d theta. Are you all still okay? You sure? What's the next thing you do? Get rid of that gravity. We're still simplifying. How much does this become? What now?
Cancel out 1c.
Cancel out.
Let's do that. So this becomes to the 3rd power. That's gone. So we'll have the 1/4 is still there. Yep, tan squared over secant to the 3rd theta d theta. What I want to know, on a show of hands, if you can make it down to that far on your own. Does the triangle make sense to you? Is it starting to make a lot of sense? Can you do that? This is the idea here, folks. This is trigonometric substitution. That's all it is. After you do this and you simplify it, that is your last section. Now this is kind of cool because we can do all of these problems. You won't be facing anything that you haven't at least seen before somewhere. I've given you some pretty tricky ones in this class, so nothing should be above you, okay? Nothing's beyond you at this point. Now, just follow the pattern. This does have tangents and secants like I told you about, but are they being multiplied?
Wrong.
Okay, so it's not sines and cosines. It's not secant tangent how we like it. It's not cotangent cosecant. If that's the case, then what are we doing with it? We're changing it to sines and cosines. So we're going to be changing this to sines and cosines if we can. Does that make sense? If it doesn't fit, change it to sines and cosines and see what you get. Right now, there's no way I'm doing that integral. I'm looking like I have no idea. There's no way. But if I change it to sines and cosines and simplify it after that, maybe we got something. So let's try it. So instead of 1/4 integral of this bunch of crap, we're going to have 1/4. This should be, I'll do this in 2 steps. This is tangent squared theta times cosine to the 3rd theta d theta. You all should be okay that 1 over secant cubed is the same thing as cosine cubed. Yes, no?
Yes.
Keep going. I don't know anything that deals with tangent and cosine to you. Was that in your trigonometric integrals from last section? No, we didn't have tangent cosine. We had sines and cosines.
Sine squared.
But if we do this, if we know the tangent is sine squared over cosine squared theta, you okay with that one?
Yeah.
do you see how changing things in the sines and cosines can really help you sometimes? Otherwise, you get stuck. What am I going to do here? Substitution ain't going to work. Try changing it in sines and cosines. Once you do that, maybe get lucky and get something that you can really work with. Here, this is really nice. Those are gone. All but one of those is gone. We have integral. Sorry, I forgot the 1/4. 1/4 integral of sine squared theta cosine theta. D theta. Now take a look at it. What would you do if you were doing this problem?
U substitution.
I would do U sub, for sure. Just so you, remember, listen, this is a perfect example of go through the patterns that I taught you. Do not immediately jump to one technique or another. Honestly, go through. The easiest thing you can do in integrals is, well, firstly, it fits the table, so we check it. Does this fit in the integration table? No, it doesn't. Can you do a substitution?
Yes.
Yeah, then for heaven's sakes, don't start doing identities and stuff if you can do a simple substitution. Does that make sense to you? So what I'm trying to get you to do is really think through these. Don't jump to a certain section because we're in it. Really think it through. We start here, we go, hey, can we do it like it is? No. Can we do a substitution? No. Is it trigonometric? No. Integration by parts? No. Trig sub? Yeah, do a trig sub. Simplify it down to whatever your trigonometric functions are. After that, does it fit a substitution? No. Does it fit any of the trig models that we have? No. Change its size and cosines. Can you do a substitution? Notice how I'm always going back to, can I do a substitution? Are you listening? We're always doing that. Always checking for the easiest, not the hardest things to do. Do your substitution. Go for it. Aren't you glad we did a substitution, didn't use an identity or something? That would have been silly, right? If we used an identity, we'd have 1 minus cosine squared, wouldn't we? Then you distribute, you'd have cosine, don't do that. What we want to have is sine with one power of cosine off to the side. If we have that already, this is the whole idea from the beginning, right? Make a substitution. Substitute for sine, cosine theta d theta is right there. So we know this is going to be 1/4 integral of this piece is our du. So this is going to be, what was it?
U
U squared.
How much easier can we get? Just don't forget about the 1/4. This follows all the way down. This would be 1/3 u to the third. Still okay so far? Okay. Now, are we done?
No.
Almost done. Almost.
Simplifying, like.
Okay, we're going to simplify. Sure, we're going to get 1/12. Do we keep the u?
No.
What's the u become?
Sine.
Okay, we're going to have a couple things to do here. So this becomes 1/12 sine cubed theta. Very good. Sine cubed theta. Now, we've already substituted once because we had one substitution here. We're done with that. We got it back in terms of theta. Look back at our integral. Did we start with thetas?
No.
We start with x's. So now that you have sine theta, can you make that back into x's?
Yes.
Where are you looking right now?
Triangle.
Use your triangle. Everyone should be able to do this. Go ahead and do it right now. Make sine theta equal to something, and then use that substitution. So I want something right here, and then I want you to substitute. So we don't even need that big. What relationship is sine, whatever what?
Opposite.
Do you have an opposite?
Yes.
Do you have a hypotenuse?
Yes.
Notice it's based on that theta. This is exactly what we're talking about here. So hopefully you should have the square root of x squared minus 4 over x. Did you all get that one? How many people did get that one? That's great. That's almost everybody. That's fantastic. So One last little step that we have. We've got a 1/12, we've got a sine to the third. So basically, all this stuff is being raised to the third power. So we get a 1/12. We get a square root of x squared minus 4 to the third. And we get an x to the third. Are you guys okay that both these are going to be raised to the third power? It's sine to the third. So this is sine theta to the third. Both numerator and denominator is raised to the third power. If you want to make it just a little bit nicer, it's really kind of up to you. I might choose to write this as this. Because that's how we were given. Do you see that? How we were... Oh, sorry, that was a previous problem. My bad. Whatever you want. You can leave it like this. You can write it like this. I really don't care.
Plus C. Oh, yeah. Sorry.
That's how I know I'm done. I never stop at integral until I either have the number, if it's definite, or I have a plus C. I need to show of hands if that made sense to you guys. Good deal. All right, fantastic. Question? Any questions? We're going to start our last problem of the section. We're going to get through the first little piece of it, and then I'm going to ask you to do most of it on your own. I think you can do it on your own. So, we're going to do the first part, though, because the first part is a little tricky, and I want to make sure you see this at least once. Last chance for any questions at all. Michael?
Over 2 to another.
I don't know.
Just for simplification purposes, before you erase it, that one right there under the triangle, can you turn that into like a 2 squared and then got rid of the radical then? Like right down one more step. That step, right there. To get rid of the radical, can you turn that into a 2 squared?
This one?
Yeah.
You can turn that into a 2 squared, but there's no way that's going to simplify that square root.
No. Alright, cool.
Don't make up your own math. It's never a good idea unless you're Isaac Newton. Who invented this? Are you Isaac Newton?
I'm not dumb.
Oh,
You got
okay.
some math ninjas now,
Me
you got
neither.
some mathematicians.
I'm Delta. No.
I'm Valentine, making my own math.
Hell yeah.
Be awesome.
He's Cupid.
It's cute.
Okay. Back
Never heard
to
that
the
one
work.
before.
Valentine, Valentino.
No, I get it.
Ooh.
I get it.
Okay, I think we can agree that looks nastier than some of the other things that we have done so far. So, first things to do.
Look at that.
First thing, I know it's fun, right? First things to do. We'll go through your whole process. Does that fit the integration table?
No.
Heck no. No, not even close. Can you do substitution?
No.
Do you understand that every time I see an integral, and I've been doing this for years, that's what I do? I'm not just following you down a rabbit hole. This is literally what I do. So I'm trying to tell you this is the best way to do it. I don't think I've got an integral wrong in a really long time. Really long time. But this is what I always stick with that pattern. I think, does it fit the table? If not, okay, go to substitution. If not, I'll write integration by parts. That's not going to work here. I don't have a product. All right, if that doesn't work, or I don't have anything that works with an ln here. That doesn't work. Does it have trig in there? Well, no, not yet. Can I fit it to something that has trig in there?
Maybe.
Maybe. Does it have a square root?
Yep. Yeah.
That's a good indication I might be able to do that. So I'm going to write this just for my own mental well-being as a square root to the 5th power. Don't forget that 5th power. Now here's the issue. This part sucks, because that part right now does not look like a right triangle. Does that make sense to you? It's not something squared plus or minus something squared, and that's what we need for a right triangle for Pythagorean theorem. So the idea is, if this, listen carefully please, this is the whole, whether you're going to get this right or wrong. If this does not fit something squared minus something squared, you make it fit something squared minus something squared, or plus something squared. So we have, let's take this off to the side, your little asterisks. 3 minus 2x minus x squared. Take a look a little bit more closely at that one. You ever heard of completing the square?
Yes.
We're going to complete the square. We're going to make this thing be a perfect square. So, how in the world are we going to do that? Well, first thing you might want to do is have this thing in order, because that's how completing the square works. So we'd probably write this as negative x squared minus 2x plus 3. You with me on that one? By the way, these are special cases. This is not going to be true for all the ones that look like this at all. These are special cases that you can actually complete the square and it'll work. So not all of them you can do this universally. I'm giving you special ones here. Does that make sense to you? Okay, so but this one we're going to see that this will. Next thing you do, you make sure that first term's positive. That's got to be the case. So what I'm going to do is I'm going to factor out this negative here. I'm going to have x squared plus 2x. I'm going to leave some space here. I'm going to leave that plus 3. You'll see why. It's completing the square. You guys okay with that one? So notice this is negative x squared, this is minus 2x, but the plus 3, I'm leaving that alone. You follow? Now, how you complete the square? You have your first term positive. You don't worry about this right now. You look just in here. We take the middle number, the middle coefficient, which is your b, a plus b, x squared plus bx plus c. Take half of it.
1.
Square it.
1.
Add it. Now, whatever you do here, you have to also undo it. Otherwise, you're changing the value of this thing. Does that make sense? But watch real carefully. Firstly, are you guys all okay with where the 1 came from? That's kind of a big deal. It's completing the square. So we go, hey, take half of this number and square it, add it over here. Now, you have to undo what we just did. I know it says plus 1, but watch carefully. We really, see how the negatives can distribute? We really subtracted 1. To undo that, we're going to add 1. So are we adding 1 twice? No, we're not. We're adding 1 here because really, when you distribute, you subtracted 1. Notice how this is going to be a minus 1? Minus 1 plus 1 gives you 0. These black letters should be gone if you were to distribute this. So if you want to check your work, if you distribute this and combine like terms, do you understand that it's going to give you this back again? It's going to be the same thing. What we've just done right here is we've completed the square. So this becomes negative x plus 1 squared. This becomes plus 4. You guys all right with that one? Completing the square, if you do this, you automatically have a perfect square trinomial. It factors. Negative, we kept that up front. This is x plus 1 squared. This is plus 4. Show of hands if you feel okay with that one. Write it in the appropriate order. We want something squared minus or plus something else squared. This doesn't cut it right now for that negative. So I'm going to rewrite this as 4 minus x plus 1 squared. Now working back to our asterisks. We got a 1. We got a square root. We got a nasty 5th power. We got a dx. In there, watch carefully. First, are you guys okay with completing the square idea? Look at what happens to us. When we plug this back in, we've got 4 minus x plus 1 squared. Do we have something squared plus or minus something else squared? Notice why it's a special case? Because if this was like a 5, it'd be kind of difficult to do. You could still do it, all right? You could, but it'd be a little bit harder. I think you can do it. I remember now. I'm pretty sure. But this is nice for us. This will be really good. Here's the next idea. I'll give it to you right now because I want you doing this on your own at home, okay? This is for you to do. You need this completed by the time we come back to classes. I'm going to rip through this thing next time in about 5 minutes. Do a substitution right now. Get rid of the x plus 1. So if you did u equals x plus 1, du equals dx, this just becomes a u. So we get 1 over 4 minus u squared under the square root to the 5th power du. U is this, so 4 minus u squared. 5th power, square root, dx becomes du. Show of hands if you can follow that one. Could you have done that on your own? Probably not before this. Can you do it now? Of course you can. Can you please finish that up for me? This is not going to be super, super difficult. I think you can all do that. Can you make a triangle with this?
Yes.
Okay, so of course, don't forget to substitute back in for u at the very end. We'll work on this next time. All right, so let's finish up our problem. As you know, what we're trying to do is we're trying to fit part of our integral into a triangle to use a trigonometric substitution on either tangent or sine or secant, because we have some nice identities with those. So we're working on our problem now, and right off the bat, we understand it's got a square root, but it's not something nice. Well, something nice is a number or a variable squared plus or minus another number or variable squared. We want something squared plus or minus something squared. That's the idea. If we don't have that immediately, don't give up on it. You might still be able to work with it. So square root is the first indication that I might be using a trig sub here. But substitution wouldn't work, of course. Nothing else will work, so we're down to just a trig sub. Square root says, yeah, you know what? You might want to give this a try with trig sub, but we got to change it a little bit. So whenever you have a case where, man, it's not obvious what this is going to be, take it up to the side. See if completing the square is going to work. So that's what we did here. We organized it. We factored out the negative. We added half of this number squared. Notice that when we add it here, it's really like subtracting it. So I undo that. So I know it's both plus 1, but because of that negative, this is really like a minus 1. So I undo it with that plus 1. We organize it again. We have a quantity minus a quantity here. We have 2 squared minus something else squared. This is our first little manipulation. Are you guys okay with that first step? It's just completing the square. I know that many of you haven't done that in a long time, but that's what it is. Maybe a review about completing the square and how to do that. Now, at this point, we could go straight to our triangle if we wanted, but to make things easy, to make it nice for me, what I'm going to do is just a very basic substitution. I want to get rid of that x plus 1. You guys follow? That way, I don't have to look at x plus 1, I'm going to look at a u instead. So whenever this is the case, when you get something squared and you don't really want to deal with it right then, feel free to do a substitution. So off to the side, I'll do u equals x plus 1. This is really easy because du is just equal to dx. I mean, it's a straight sub. It's nice. If you're getting like, after your derivative here, something in terms of x, yeah, don't do that. Just the constant is what we're trying to get out of that. Does that make sense to you? So here we go. All right, cool. Well, we got an integral then. We got 1. We still got this bracket with a square root. We got a 4 still. But here we're just going to do minus u squared to the 5th, and then du, straight substitution for dx. Now this looks a little bit more manageable. So right now, what do we do? Yeah, we're going to do that triangle. It's a square root. It has something squared minus something squared. That's fantastic. So right here, I'm going to take my square root. I'm not going to think about it as 4. I'm going to think about it as... Yeah, that gives me the length of a side or a hypotenuse, or I'm sorry, a leg or a hypotenuse, depending on what we're given and which order we're given. And I'm going to draw my right triangle from this. What I definitely don't want to do is leave that at 4 and mistakenly put 4 here or here or here. Then my integral's going to be all screwed up. I'm not going to get this thing right. So I really want to make sure that we understand that this number is the length of a hypotenuse or the length of a side, a leg, squared is what that is. So right triangle, always drawn in the same orientation. That way we always have this thing right. By the way, what is this thing? Is this whole thing the length of a leg or the length of the hypotenuse? Yeah, how do you know? Yeah, the minus right there. This says what this is. Which one of these pieces is the hypotenuse then?
The 4 bigger ones, the 2.
The 2, not the 4, but the 2. So the 2 is the hypotenuse. The first one is the bigger one. Otherwise we'd get something negative inside of the square root. We can't have that. So if the 2 is the hypotenuse, the only way this comes about is if I take the hypotenuse squared minus another leg squared and took a square root of it. That says this piece is one of the legs. Now, we just have to be really good about fitting the legs in the right place. We want a trigonometric substitution that works. It's got to be sine or tangent or secant. So, which one's going to work for us? Would tangent be a good choice? No, heck no. I want to deal with the 2 at some place, right? So it's either going to be sine or it's going to be secant. However, I want the 2 to be on the denominator. I want the constant on the denominator of whatever fraction I'm going to create here, whatever relationship. So
Sine.
it's going to be sine, which means x goes opposite or x goes adjacent.
You.
Make it so this stuff works for you. Don't make it...
It's you.
It is me. Yes, I know.
Seen it for a week.
It's not me, it's you. Anyway. And we have the square root of 4 minus u squared. That's right, I did the substitution, so I have u now. So you guys feel okay with that one? So we go, hey, hypotenuse, no problem, it's 2. This stands for a leg, just put it in the right spot so that we get u over a constant for whatever trig sub we're going to do right now. What's the appropriate one again?
Sine.
Yeah, sine's going to give us u over 2. Sine theta, so sine theta equals u over 2. And then we're going to do what? Solve for u, okay, so u equals 2 sine theta. And next step, what is that? Sure, because we're going to do a couple things here. We're going to substitute for our u. We're also going to substitute for our du. I think hopefully we're all okay with the derivative of 2 sine theta being 2 cosine theta. No product rule, nothing like that. Now we get to put this back into our integral and make it a lot nicer looking, well, not nicer looking, but easier for us ultimately. It's going to look nasty at first, you know, oh my gosh, there's stuff everywhere, but it'll all simplify for the most part. So we got a 1. What's going to be inside of our square root right now? Can you tell me please?
4 minus 2 sine theta squared.
And if you do 2 sine theta squared, that should all be in parentheses. And then this whole thing is raised to the 5th power. And then finally, I do got to remember about my du. Some of you guys are forgetting some of this. I can't have you forget this. Du has to be substituted for. So instead of du, we're going to put 2. Perfect. Okay, let's make sure we got this. 1 stays, 4 stays, minus stays. U, no. U is 2 sine theta. We got it. We have it squared. We have 2 to the 5th power. Du, no, not du. 2 cosine theta d theta. D theta's got to match everything. We can't have 2 different variables up there, otherwise that doesn't work for us. So far so good? Now what do we do?
Square 2, pull it out.
Yeah, we're going to simplify as much as we can. We don't start any sort of substitution right now. That'd be crazy, right? I mean, how are we going to do that? What we do want to do is, well, simplify it as much as we can. Change it into an integral that we know how to do. So 1 over, if we do this, this is going to happen a lot for you, where you have 4 minus the same number, whatever number it is, and then sine squared theta to the 5th power. Are you still okay? Okay, awesome. What now?
Factor out the 4.
We're going to do the 4. We got to have this as 1 minus something for this. Otherwise, you know, we got 4 minus 4 sine squared theta isn't an identity. 1 minus sine squared theta is. So we're going to factor that. If we factor out the 4, just be careful with your algebra. Don't do all of this stuff in your head. Give yourself some time to really think about it. I don't want you just pulling out a 2 and have a 1/2. You really need to see that what's going on here is, well, we're pulling out the 4. Yeah, the square root of 4 is 2. So we factor out the 4 and take a square root. It's 2. We still have a square root of 1 minus sine squared theta. Are we all okay with that one?
Yeah.
Factor the 4. We can separate square roots by product. Square root of 4 is 2. No problem. It's outside the square root. This is inside the square root. But it's still being all raised to the 5th power. So don't do something silly right now and cross out this 2 with this 2. Order operation says you do exponents before you start simplifying things like that. Well, what that means is then we got an integral. We got 2 cosine theta.
Oh, you're doing it all at once.
We got 2 cosine theta. What's that 2 going to become?
32.
Yeah, because it's 2 to the 5th power. So we got 32. And then we got 1 minus sine squared theta. Yeah, to the 5th. D theta. We're going to do a couple steps right now. What's the first thing we're going to do?
Pull out 1/16.
Yeah, 1/16 goes up front.
Use the Pythagorean identity.
So this is 1/16. We got it. We got a cosine theta. This is why we did that substitution for sine, because we knew it was going to be 1 minus something squared. Well, that something squared's got to be sine for this to work for us. So 1 minus sine squared, well, it gives us the square root. And that's all raised to the 5th power. Notice how I'm writing lots of steps. I'm not trying to do everything in my head right now. I know you guys are smart. I know it. But I don't want you doing everything in your head, because what if you forget a little constant? Is that going to be a good thing? No. It's a bad thing. If you forget a little square or a fifth power, that's a bad thing. I don't want that to happen. Square root of something squared.
Itself.
Awesome. So I'm going to have 1/16 integral of cosine theta. Let's do this at once, okay? This gives you cosine theta
Cosine
to the fifth power.
Yeah.
1/16 1 over cosine to the 4th theta d theta. Now, before you start working with this integral the way it is, 1 over cosine to the 4th, it's probably a good idea to check if it fits one of our integration models first, which means that when I'm looking at that, I'm not thinking 1 over cosine because I don't know what to do with 1 over something, do I?
No.
I know what to do if this was cosine to the 4th. That'd be great. I'd split it up as cosine squared squared. I'd do 1/2 times 1 plus cosine 2 theta squared. I'd distribute. I'd do that again. But it's not that. It's 1 over cosine to the 4th. So let's change that into a trig function that we know how to do it. So 1/16 integral of, let's talk about this as secant to the 4th theta d theta. And fortunately for us, we know what to do when we have secant to the 4th power, when secant is even. Think back to your trig, to your last section. What do you do when secant is even?
Break it up to a secant squared.
That's right. So we're going to take a secant squared out of there. So 1/16 secant squared theta times secant squared theta d theta. The reason why we do that is because we're trying to get a tangent. If we get a tangent by some sort of a Pythagorean identity here, then derivative of tangent is secant squared. So the reason why we break out the secant squared is because we're looking for a tangent from the rest. That's why we did that with even powers of secant, because with even powers we can strip off the secant squared. It's still even. We'll be able to get an identity of 1 plus tangent squared somewhere in there, if I'm right. Hopefully, identity. Now, I'm going to have to erase part of this. Do you have any questions on this before we continue? So you got all this written down, right? This was basically just an algebra, completing the square and then doing one basic substitution. One thing I do want to remember is this, okay? I'm going to leave this on the board because this was kind of big for us at the very end. And I'm sure going to leave this on the board. So 1/16, no problem. Integral, looks like we're going to have, what do I change that secant squared into? What's that going to be?
Tan squared.
Plus, or 1 plus tan squared theta, whatever you want to write that as. Times a secant squared theta d theta. Look how everything, what this does, it changes it back into some sort of a trig model that we know how to deal with. That's what our trig sub does. Changes something we know how to do. That's what substitutions always do. Change it into something we know how to do. Yeah, no, it's kind of basic after this. We know a u sub for tan theta. We've already dealt with this stuff. du equals secant squared theta d theta. That's right here. That's exactly what we wanted. That's why this stuff worked. Oh, what I forget?
So we can, no, I think, I was just wondering if we can.
Oh, you know what? Yeah, we have a u. You might want to change it to a different variable. So I already used a u, so that's a good point. Forgot about that one. Let's make this into like a w. Just so we don't get confused, because we will be resubstituting back in for u, and I don't want any confusion there. So good point. Thanks for catching that. I saw the look on your faces, and wait a minute, wait, Mr. Lannerford, yeah, I made a mistake. I mean, I was testing you. You passed.
Making sure we're awake.
That's right, and making sure you're awake. That's the age-old excuse for mistakes from math teachers. So integral, tell me what's inside my integral right now, please. What is it?
U squared plus
W
squared.
Not u.
W.
W squared plus 1.
Yeah.
dw.
Good. This whole thing is dw. Whole thing is dw. Yeah, let's do it. Let's integrate. Can you all do that?
Yes.
Push can. So when we integrate here, we've got
1/3
W third over 3 or 1/3.
Plus W.
Okay, that looks pretty painless, but we have some things that we're gonna do. We've done 2 substitutions here. So, first thing we're gonna do, we had W's here, we started with some thetas. Originally we started with X's, so we're gonna have to translate this back twice now. Firstly, I wanna make sure you're all okay with this so far, show of hands if you are. After this point, it's pretty easy. I mean, it's stuff you know how to do, so just do it like we've been doing. Okay, so we're gonna have 1/16. We'll have 1/3. Well, what's that W become?
Tangent cube theta.
So sure, tan cubed theta plus how much?
Tangent.
Theta.
We still okay?
You gotta put your X's back in.
Okay, so we are gonna put X's back in, but it's kind of weird. We've done 3 substitutions. We substitute first with a U, then we made U's into thetas, then we made thetas into W's. So now
Theta.
we've got our W's, we got them back into thetas. We're going to use this to translate our thetas back into U's, then we'll use this to translate our U's back into X's. Does that make sense to you? All right, so as long as you have your breadcrumbs to come back with, you'll be fine. All right, just don't forget this stuff. We don't want to get too involved in this to forget what we actually started with. So with here, we got 1/16, going back up top. 1/16. We got 1/3. Let's think about tangent. Can you figure out what tangent is? Tangent theta is? That's why we leave our triangle here. This is theta. So tan theta is
U over square root 4 minus U squared.
Over plus.
cubed, the whole thing. Plus. Can you do tan theta? Same thing, but not cubed. You know, I'm gonna change that to a parentheses just so it looks a little bit better. By the way, is it the 1/3 that's also getting cubed or not?
No.
Okay, that wasn't inside there, it's just the tangent. So tangent of theta, hey, look at that. Tangent of theta is U over this guy, square root of 4 minus U squared. No problem. We got it to the 3rd power. Plus another tangent. Same idea, opposite over adjacent. It's right there. Are we done?
No.
One more thing to do. Now, at this point, if you are going to choose to simplify this, this is where you would do it. Okay, you try to make one fraction out of this right now, instead of plugging in x's first, all right? So we get all the way down to as simple as we can with u's, then we plug in the x's. Does that make sense to you? So if you choose to do that, so this may or may not look like what it is in the back of your book. It might look different. They might find a common denominator here. It wouldn't be super hard to do. You'd multiply this by 3 and another 4 minus u squared factor, and you can find a common denominator, get one fraction out of it, and then you plug in your x's. You follow? That's the idea. Now, for the sake of time, I'm not going to do that. I usually do on this problem to show you how insane it gets with your algebra, but I'm not going to. That's going to be on you. What I'm going to do is do one more thing. What am I going to do?
Using the X.
Are we still keeping the 16 outside?
You can distribute it, you can keep it outside. I'm going to keep it outside just for the sake of seeing where everything's coming from, okay? Again, if you were to simplify this, you would do it here before doing what I'm doing right now. Because otherwise you have a lot of different factors, a lot of different terms of x plus 1. You're changing every u into 2 terms. That gets kind of crazy. So we'd have an x plus 1. We'd have 4 minus x plus 1 squared, and then that's under square root, and this whole thing is raised to the 3rd power. Then we'd have another x plus 1. We'd have 4 minus x plus 1 squared. That's too small. And that's what we would deal with.
Let's see.
Let's see. Let's me know on that. Did you get it?
Yeah.
Could you follow it?
Yeah.
Do you want to simplify this one and see what you get?
No, sir.
You sure? We can do it if you really want to.
No.
Do you know how to?
Yes.
No. For some of you, sadly, that's true. Oh, good. It kind of makes me want to right now.
Go for it.
Go for it.
Yeah.
First you say no, and
Yeah,
I know, and then I just completely said, I'm going to anyway. Forget you guys. Let's see. If I were to do this, here's how I would do it. I would think of this as u cubed over 3 square root of 4 minus u squared to the third. I would multiply this by 3 and 4 minus u squared squared on both the numerator and denominator. That would change it to a third. If you simplify, you can see that I'm right. This would cross out all but one of those. This would cross out, you'd have just the u. So this is the same. After that, you do a little bit of simplification. We'd get 1/16. We'd get u to the third. You'd get 3, bunch of junk. To the third. This right here, square and square root are gone. We get plus 3u times 4 minus u squared. You still with me? You catch me if I've made a mistake. Sometimes this happens. It happened to me once, earlier today. After that, 1/16, we'd have a u cubed plus 12u minus 3u to the third over 3 square root of 4 minus u squared to the third. After that, combine your like terms if you can. I got a 1/16. Doesn't really matter how you do this, but I'm going to have a 12u minus 2u to the third over same stuff. That's as simple as we can make it, right there. The only, not as simple, we could factor out a 2 if we really wanted to. That might be a good idea. So if we factor out a 2, then what we would get is 1/8. 6u minus 2u to the third. Say what?
Why did you say 2
You wrote it right, but you said it wrong.
Yeah.
What'd I say?
You said 2 to the third.
Well, obviously it's just
Well, the
you.
camera was on the way. I didn't see.
You told us to catch your mistake.
You did, yeah. Okay, that's as simple as we can make it. Well, not really. We can factor out the 3 too. That'd be easier. 1/24. Let's just do that here, okay? We'll get rid of this 3. We'll make that a 24. Are we still okay so far? Is all my algebra right? I certainly hope it is.
Let's see.
Not yet. We're going to do the x's. Bless you.
Thank you.
Bless you. At this point, when you've had it simplified, here's where you plug in x plus 1. So 6, x plus 1, because u is x plus 1, minus x plus 1 to the third power, all over 4 minus x plus 1 squared, square root to the third.
We could get rid of the square root on the bottom.
We can't. No, we can't. We still have the square root. What I'm gonna leave this. I'm gonna leave this as 3/2 power. I am gonna simplify this one because I want to show you that what you're gonna get back is exactly what we started with. 3 minus 2x plus x squared, or minus x squared. It's gonna be the same. So if I do this, this would be 1/24 we got a 6x plus 6 minus, if you're going to distribute that, it's x cubed plus 3x plus, I'm sorry, 3x squared plus 3x plus 1, but that's inside parentheses. Here we got square root of 4 minus x squared plus 2x plus 1 in parentheses. Be the third. Moving on, distribute your negative and then we'll combine some like terms. Almost done. So let's see here, we've got a 5, we've got plus 3x, we've got a minus 3x squared, and a minus x cubed. Can you double check my combined like terms for me, please? Yes, no?
Plus, you know.
Now it's a plus. Thank goodness.
So, this is on a test that.
So I want this, all right?
No.
All right, I just want you to see what potentially you can get out of this thing. We stopped right here. You need to see that this and this are equivalent by algebra. They're the same thing. So can your answer look a little different but be the same?
Yeah.
Yeah, this is simplified. Though actually it's not. You can actually factor out an x plus 1 here. So if you factored that out, then it would be simplified. But that's the idea. Show of hands feel okay with the idea. All right. Take a deep breath. We're done with trig sub for like 10 minutes. Well, here's the point. You now have a whole bunch of integration techniques, right?
Yeah.
We know substitution. We know integration by parts. We know how to do trigonometric integrals. We know how to do a trig sub. All those play of, we know integrals of inverse trig functions, right? And hyperbolics and all that stuff. All those things play a part in the following sections. All of them. We're going to use all of them. That's why we did integration techniques, so that when I give you an integral, you can do it. There's only one more integration, I think one more integration technique that I'm going to teach you. It's this next section, 7.4. It's much more algebraic than the stuff we've been doing. There's not a whole lot of trigonometry in it unless you have to use a trig sub for part of it. You got me? And that will rarely happen because what we're going to deal with in this case are rational functions, integrals of rational functions. Any questions at all before we continue? You sure? This made perfect sense to you? Perfect sense? Perfect sense up to here?
I'd love to take a picture and show